So, welcome again. So, in the last lecture, we stopped at the point where we got two equations. One was derived using the difference in energy, which was given by epsilon T minus epsilon naught, which is the difference between the energy at finite temperature T and the energy at zero temperature. And we also used the fact that N by V is given by some integration. So we use the formula for the number density of electrons also. Just not saying it, I'm also writing it. So we left at the point. So we wrote. So this is electron electron specific heat. So stop that. So we got two equations, which were first, the difference in energy is your, this is integration 0 to EF epsilon k G of EK Fermi Dirac epsilon k minus mu finite temperature chemical potential D of EK plus the other interval epsilon F to infinity epsilon k G of EK Fermi Dirac epsilon k minus mu D of EK. So guys, in between I'll be switching between epsilon k and EK. So just pardon me, I just keep messing the terminologies. So it's basically the energy, right? So this is minus 0 to EF, the remaining portion, which is the energy at zero temperature. So this is EK, G of EK, D of EK here, the Fermi Dirac distribution. Below the Fermi energy is 1. So it's 1 in this interval, in the energy interval. Alright. So this was our equation 1. Alright. Now we had another equation. Which is epsilon F to infinity epsilon F G of EK Fermi Dirac epsilon k minus mu D of EK is given by 0 to EF G of EK D of EK minus 0 to EF epsilon F G of EK, the Fermi Dirac distribution. Now this is easy to see that we can simplify it further. 0 to EF G of EK, and this is 1 minus Fermi Dirac epsilon k minus mu D of EK. All right. So this was our original equation 2. So now what we are going to do is we are going to rewrite equation 1 and just do a simple manipulation from 1 itself. Your delta E is given by 0 to epsilon F. The first part we keep it intact. G of EK, the Fermi Dirac epsilon k minus mu D of EK. Now, instead of writing EF to infinity EK, we write EK minus EF. G of EK Fermi Dirac EK minus mu D of EK. Now, as we included a negative EF term, so we have to accordingly add also. So this is EF to infinity epsilon F G of EK for Dirac epsilon K minus mu D of EK, and the term that was already there 0 to EF EK G of EK D of EK, sorry. So D of, right, D of, all right. So now you have to use equation 2. Using equation 2, all right, because you've already got the value of epsilon F to infinity EF G of EK F D EK minus mu D of EK. So this is this term. Use 2 here, right? So this will be very lengthy. So, but anyway, let's just do it. So this is 0 to EF EK. So the bookkeeping stuff here is very important. You need not forget any term that will be detrimental to the result. So EK minus mu D of EK plus epsilon F to infinity G of, sorry, epsilon F to infinity. We had what we had epsilon K minus epsilon F G of EK for me Dirac epsilon K minus mu D of EK. All right. So now substituting the equation 2 in place of this equation 1. So this is 0 to EF G of EK 1 minus Fermi Dirac epsilon K minus mu D of EK minus 0 to EF. This term was already there. G of EK D of EK. All right. So now you'll start to see that there are common terms that we can jot down together or we can couple together. So if you notice, this is 0 to EF minus EK. So this term, so let me just point out by just putting, to indicate these markers. So this term and this term will couple together. So this is, sorry, so this is your epsilon F minus epsilon K G of EK D of EK. Simple to understand. Now you have this term and this term. Both have limits 0 to EF. So it's easy that you separate out those two coupling terms. So minus, because EF was in front, to keep track of things, you should put a minus. So EF minus EK G of EK, then Fermi Dirac EK, your Fermi Dirac EK minus mu E of EK. All right, and one term is left, and which is plus EF to infinity. Only one term is left, which is this term, which is this term, which is EK minus EF G of EK for Dirac epsilon K minus mu D of EK. Fair enough. So if you see that we can use the first two terms as two common terms. So let me just write. So 0 to EF, epsilon F minus epsilon K, G of EK, and 1 minus Fermi-Dirac epsilon K minus mu D of EK, and the term EF to infinity, just bookkeeping stuff. But it's very important that you do the bookkeeping sincerely, because this is prone to making mistakes. All right. So now we are somewhat relieved. All right. So this is the final form that we get. All right. So this is what we get. Now what we are willing to calculate is the specific heat. All right. So this is the specific heat. So specific heat definition is CV is DE DT. All right. So now if you see all these terms that we have calculated in the last line, none of those terms like EF, EK, G of EK depend on temperature. What? Obviously, FD, which is the Fermi-Dirac distribution, does depend on temperature. So FD depends on temperature. Understood? Good. So CV will then be given by minus 0 to EF, because the first term is temperature independent. So the second term will stay. Now G of EK D Fermi-Dirac. I'm not writing the arguments reiteratively. DFD dt D of EK. All right. Plus EF to infinity EK minus EF G of EK D FD dt D of EK. All right. So now this term, it has minus in front. Then put the minus inside, and what we get is EK minus EF G of EK D Fermi-Dirac dt D of EK plus epsilon F to infinity EK minus EF G of EK D Fermi-Dirac dt D of EK. All right. So now you see that this is so simple that you have the basically same term. All right. So this is just two intervals of the broader interval. We incidentally we see that we have a result where the integrand is same, but the two intervals are just splitted up intervals of the greater interval. Like say, let's from 0 to infinity, we divide it to 0 to EF and EF to infinity. So this is very simple to write. So this is 0 to infinity EK minus EF G of EK D Fermi-Dirac dt D of EK. Therefore, CV is this. So this is your CV. Now, here comes the time that we make an approximation. All right. So let's get back to our earlier knowledge that this energy levels are filled up with electrons. All right. These energy levels are filled up with electrons. So the Fermi energy will be up to this level. All right. So if you supply kBt of energy, only those electrons that are in and near the Fermi energy, only those electrons will be excited, which we repeatedly said in the last lecture, because the innermost lying electrons will find no vacant energy levels to go into. All right, so just briefly write this. Only those states which are within, you supply a kBt of energy within kBt of EF will contribute to Cv of electron gas. All right. So only those states. So this will be transferred to the higher energy levels. And as we said, there will be an increase in the mean average energy of the system. So G of Ek will get contributions from electrons around EF, hence contribute to specific heat as essentially G of EF. So you can safely write that G of Ek as G of EF, because only those electrons around the Fermi energy will be excited to higher energy levels, and in and around the Fermi energy, kBt of energy within spacing kBt of the energy level around the Fermi energy, the electrons will be excited. So in principle, you can write GEK as G of EF. Why this is so? Because you already studied that kBt is much lesser than the Fermi energy. This Fermi energy is in orders of electron volts, and if you write Fermi energy as Kb T of F, P of F Fermi temperature is of the order of 10 raised to 4 Kelvin. In comparison, T, if you heat it up, like you heat up the sample to let's say 100K or so, this is still 2 orders of magnitude smaller than TF. So what you essentially have now is that you can write 0 to infinity Ek minus Ef G of Ek d Fermi Dirac dt d of Ek as G of Ef 0 to infinity Ek minus Ef d of Fermi Dirac dt d of. All right. So now what we are left with is just the differentiation of the Fermi Dirac distribution. So the Fermi Dirac distribution is Fd Ek minus, this is still new because you are considering energy levels that are excited at a finite temperature. This is not the problem at temperature T equals 0. So this is still Ek minus mu. So the Fermi Dirac distribution is given by 1 Ek minus mu over kBt. All right. So now this is routine differentiation, which will be given by dt of your 1 plus e raised to, so 1 plus so 1 plus e raised to Ek minus mu over kBt times -1. So this will be -1 times 1 plus e raised to ek minus mu over kbt minus 2 times the differentiation of the exponential, and this is ek minus mu over kbt squared. Minus will come from this, so this will be 1. So your d permitted dt is kb epsilon k minus mu over kb squared t squared e raised to ek minus mu over kbt by 1 plus e raised to ek minus mu over kbt squared. All right. So now CV is your kb g of ef, integration limit is 0 to infinity. So ek minus mu was already there, so kbt whole square e raised to ek minus mu over kbt divided by 1 plus e raised to ek minus mu over kbt square. D of ek. Now you have to make a substitution. Let ek minus mu by kbt is your x, implies dx is equals to 1 over kbt times d of ek, implies d of ek is kbt times d of x. All right. So earlier we used this formula g of ek for me derive epsilon k minus mu d of ek is similar to g of ek for me derive mu k. Sorry, this is ek minus mu d equals 0 d of ek. As the number of electrons are constant, as the number of electrons is constant, it doesn't depend whether you calculate at t equals 0 or t not equals 0. That is a finite temperature. So I'll not go deep into this, but extension of this integration, similarly following this integration process, will have that mu at finite temperature t is given by mu at t equals 0 plus some terms of the order of t by tf whole squared. So mu at temperature t is given by mu at temperature t equals 0 plus some terms that depends on t by tf squared. So we already estimated that t by tf is of the order of 10 raised to minus 2. Squaring it will be 10 raised to, sorry, squaring this term will be 10 raised to minus 4, which is even smaller. All right. So now the physical picture is like this. This is Fermi Dirac. This is your ek. This is 1 till 49 temperature. This is your EF. So this is at t equals 0. But at t not equals 0, see that there is a spreading of the Fermi Dirac distribution. So this is at t not equals 0. This is the Fermi Dirac. This is epsilon k. So now earlier it was here. The Fermi Dirac distribution was positive value or a finite value that is beyond that equals 0. But now the Fermi energy is here. So this is F, EF, and this is, so you can notice that mu T is greater than mu naught at T equals 0. So this is the picture that you should keep in mind, which is already taught to you. So now what you can essentially write is that as the higher order terms, this T by Tf square, this is negligibly small, you can essentially write mu at T finite temperature T as an approximation. You can write this as mu at temperature T equals 0, which is basically the Fermi energy. This greatly simplifies our specific form, because in the exponential, as you can notice, that you have Ek minus mu. All right. So we had Ek minus mu. So basically, you can transform that Ek minus mu as Cv. Cv is Kb g of Ef. All right. 0 to infinity Ek minus Ef squared by Kb t squared e raised to Ek. So writing all those mu as Ef by Kbt divided by 1 plus e raised to Ek minus Ef by Kbt whole squared d of Ek. All right. So we already did the substitution with Ek minus mu as x. So basically now, with in place of mu, just put Ef and employ the same substitution. So here let Ek minus Ef by Kbt as x, implying Ek is Kbt dx. So now Cv becomes Kb squared T g of Ef x squared e raised to x by 1 plus e raised to x whole squared dx. Just you can put the, now you can put the limits. So when Ek is 0, x is minus Ef over Kbt. And when Ek is infinity, x also tends to infinity. But remember, this Ef is Kb Tf by Kb T. So essentially Tf by T. This is at least 10 raised to 2 orders of magnitude greater. So this is, in principle, this is very, very large. So now if you put the integrand, the value of minus Ef by Kbt in the integrand, let's say x squared e raised to x 1 plus e raised to x whole square. So x is minus Ef over Kbt. You can essentially treat it to be minus infinity, as we know that Tm by T ratio, this is very, very high. So you can essentially treat it as minus infinity. So what this does is x squared e raised to minus infinity 1 plus e raised to minus infinity. So this is x squared e raised to minus infinity by, in the denominator it basically goes down to 1. So x squared into e raised to minus infinity, this is c. So even if you put minus Ef by Kbt, it will be very, very large in the negative direction. So there's no harm in taking that to be the limit minus infinity. All right. So your Cv, just even now a simpler form, Cv is now Kb square T g of Ef minus infinity plus infinity x squared e raised to x by 1 plus e raised to x whole squared. This is dx. Turns out that this is a known integral. So this is a known integral in mathematics, and this gives pi squared over 3. So our CV is pi squared over 3 AB squared G of EF times T. So now you see the bigger picture, because after so many excruciating derivations, you see that what we have been talking about for so long, that the specific electron specific heat at very low temperatures is linearly dependent. So this is the proportionality constant. So this is the proportionality constant, and this is your P. So this implies that CV is proportional to P. So now in this lecture, what we found out is that we derived the specific heat of the electron gas, which comes out to be proportional to T, linearly dependent on T. So let's just stop here, and we will see the repercussions of this electron specific heat, which linearly depends on temperature. All right.